In previous slides, we've looked at the ways in which ions can react with one another. Initially, they're separate from one another in completely different beakers. Combine them, let them occupy the same space, and cations are going to be attracted to anions that weren't present before. And in some cases, they'll come together and form an insoluble solid that'll sink to the bottom of the container, just as you see here in the picture. In other cases, the ions may not be interested in each other whatsoever. Say a cation and another cation. Well, they're going to repel, and obviously they can't be combining in any way. Same goes for two anions. And then our solubility rules tell us also that there are some combinations of cations and anions that, although they may be attracted to one another, they still are soluble in the solution, and therefore they don't form solids. What we're going to do next is we're going to look at a chemical reaction that we've already looked at, and we're going to attempt to describe in detail the chemistry that's going on in the form of a chemical equation. The reaction that we're going to look at, just to review with you, is one that involved sodium carbonate and calcium chloride. You should recall that as we considered the possibilities, the sodium combining with the chloride, the calcium combining with the carbonate, or maybe the sodium combining with the calcium, there was only one possibility for the solid that formed. We needed to combine a cation with an anion, and the cation was going to be the calcium, and the anion was going to be the carbonate, and the two of those come together to form the calcium carbonate solid. The remaining ions, the sodiums and the chlorides, well, they continue to roam around within the solution and float freely. We can write this as a chemical equation by writing what's known as the molecular equation. Here you see the chemical formula for sodium carbonate. Notice that it's AQ. This is really an important feature. You see, if something is noted as AQ, aqueous, we know that it has already dissolved in water. The calcium chloride also is aqueous, and so the calcium chloride solution was clear, colorless, with the calcium and chloride ions floating freely in the bulk of the solution. But you take these two aqueous solutions and you mix them together, and you form a solid. We identified that solid earlier as calcium carbonate. Hence, we have the parentheses and the letter S down there in the balanced chemical reaction. Furthermore, there are sodiums, of course, and chloride ions. There are two, in fact, sodiums and two chlorides, and these would combine and be written as NaCl. But since they didn't form a precipitate, well, what we'd have is the AQ, the aqueous, telling us that they are really dissolved in water. The molecular equation is something that includes as much detail as is possible in the most efficient way possible. We have another type of chemical equation, though, that we use to explore the nitty-gritty details of what must be going on here, and it's called the total ionic equation. Now, in the total ionic equation, we spare no expense. We show all of the details. And what we do is we begin first with the sodium carbonate, and we note in our minds that it's a soluble salt. It's aqueous. Therefore, what we're going to do is we're going to expand sodium carbonate to show every single one of the ions that's produced. Sodium carbonate breaks up into a total of 3 ions. One sodium, another sodium, after all, it was Na2, and then the carbonate ion. Now, each of these is still aqueous, and in fact, in real life, these sodium ions and carbonate ions are floating freely within the solution. We just chose to write it Na2CO3 in the molecular equation because it was more efficient, cleaner, requiring less space. The bottom line here is that whenever you see something that is AQ, if it's an ionic solid, you're going to be able to write it as ions. And we've got another one of those coming here. The calcium chloride, CaCl2, well, it's aqueous too. That means that we ought to be able to write each and every one of those ions individually in the total ionic equation. And of course, we'd have first the calcium ion, and then follow that with the 2 chloride ions. Now, a little bit different from the sodium carbonate that we wrote just a moment ago, I've included a coefficient here in front of the Cl- to save on some of the space. The 2 Cl- really means a Cl- and another Cl-. But we can do some cleaning up, even with the total ionic equation, as long as we understand that a 2 out in front of the chloride ion means that we have 2 of them. Okay, well that about wraps up the reactants. Let's take a look at the products. We've got calcium carbonate, and it is a solid. Since it doesn't dissolve, the calciums and the carbonates are locked together in a crystalline lattice. And because it is a solid and something that is unified and not something that splits into pieces, we're forced to write it as simply calcium carbonate solid. The bottom line here is that you can only break up things that are aqueous. Only aqueous species in a total ionic equation can be broken up into ions. Gases, liquids, and solids must appear with that subscript, gas, liquid, solid, and cannot be broken up. We're not finished, though, with the products yet. The 2 sodium chlorides are aqueous, and so from those we will get 2 sodium ions that are aqueous and 2 chloride ions that are aqueous. All right, so you can see that the total ionic equation contains a lot of detail. You might also notice that the total ionic equation contains a fair bit of redundancy. That is, things that appear both on the left and things that appear on the right. When an ion or a species appears identically on the left and on the right, we call those spectator ions. They're present in the solution, but they're not changed during the reaction at all. And we have certainly some spectator ions in this example. For example, look at the sodiums. On the left-hand side, okay, they appear in 2 different places, but we can still sum them up and say that we have 2 sodium ions on the left-hand side as well as 2 sodium ions on the right-hand side. The sodium ions, well, they're spectator ions. Are there any others? Look carefully and you'll see that there are. The chloride ions are also spectator ions in this case. They appear both on the left-hand side as reactants and on the right-hand side as products. And so both sodium ion and chloride ion are spectators. Identification of the spectator ions lets us write down the next type of chemical reaction, and that will be the net ionic equation. The net ionic equation is exactly the same as the total ionic equation. These two are exact duplicates of each other, except that for the net ionic equation, we don't write down the spectator ions. And so in this case, the spectators, the sodiums and the chlorides, won't be included when I write down the net ionic equation. Well, what am I left with? Well, I'll have the carbonate, and I'll have the calcium on the left-hand side, and on the right-hand side I'll have the calcium carbonate solid. So remove the spectators, there's a calcium, there's the carbonate, and finally there's the calcium carbonate solid. You see, the net ionic equation is something that really zeroes in on exactly what important things are going on in that reaction. The sodiums and chlorides, oh, they were along for the ride. They float around before, they're floating around afterwards. They don't get changed chemically. But the calcium and the carbonates, why, they pair up. And when they do, a solid forms. And so the essence of the molecular equation is the net ionic equation that really shows us clearly what things are coming together and what products are formed as a result. Now you may wonder then, with all this talk about spectator ions and the fact that we didn't include them in the net ionic equation, were they really necessary? Were the sodium ions and the chloride net ions really necessary for this chemistry to go on? And the answer is yes. Whenever we deliver an ion to solution, be it a cation or an anion, we need to deliver it with its partner, its oppositely charged species. In the case of the sodium carbonate, we needed carbonates. After all, they later went on to form a solid, but to deliver them to the solution, we needed to pair the -2 charged carbonate with 2 positive charges from sodium to keep the combination neutral. You see, in the back storeroom, we don't have bottles of sodium ions. We don't have bottles of calcium ions, because those bottles would have a net positive charge in the case of those 2 ions. In fact, what we have in the back storeroom are bottles of sodium ions and chloride ions, table salt, ions that are already paired to maintain electrical neutrality. Those spectator ions are important. Without them, carbonate could not have arrived at this chemical equation, and neither could calcium. But after they're in solution, after they're floating around freely, the responsibility or the importance of the spectator ions is no longer necessary, and what becomes important are the ions that actually combine to form something new, like the calcium carbonate solid. Now let's look at a different chemical reaction. We're going to treat this one in the same way as we did the previous example, where we'll be writing down molecular equations, total ionic equations, and net ionic equations. The reaction that you see before you is a classic. It's an acid-base neutralization reaction. The acid's the sulfuric acid, H2SO4. It's a strong acid, and you should know that it's a strong acid. It's actually a strong electrolyte. Sulfuric acid conducts electricity like crazy. Why? Because it contains all kinds of ions. Sodium hydroxide is the base in this case. And the two, sulfuric acid and sodium hydroxide, will react with one another as part of this acid-base neutralization reaction, producing one of those key signatures for acid-base neutralizations, namely water. And in this case, we'll get 2 moles of water, and you see it there on the product side. Another thing that comes along will be, well, whatever's left over. And we'll have 2 sodiums left over, and we'll have that sulfate from the sulfuric acid, and that's going to give us sodium sulfate, Na2SO4. As you look across, pay special attention to those things that are aqueous and those things that are not. Anything that's aqueous, we should be able to split up into the ions that it really represents. So as we attempt to write down the total ionic equation, let's first look at H2SO4. It's aqueous. We recognize the 2 hydrogens, and we recognize the SO4 sulfate polyatomic anion. And so we're going to get 1 hydrogen ion, another hydrogen ion, and a sulfate. And all 3 of these are going to be aqueous. This is really what's in that bottle of sulfuric acid, a collection of 2 hydrogen ions for every sulfate polyatomic anion. That's what's really there. The sodium hydroxide, well, that's aqueous as well. And in the same spirit of things, we can break sodium hydroxide up into the ions that it's made up of. And in this case, we would have 2 sodium ions. After all, it was 2 NaOH units, as well as 2 hydroxide polyatomic ions, and I'm showing them there for you. All right. Again, that total ionic equation shows us in excruciating detail every single ion that is possible in floating around in that solution. We continue this process out to the right into the products. But remember again that only aqueous species are those things that we can break up, and so the 2 waters, they aren't changed. They're liquid. They appear just as they were in the molecular equation. To wrap things up, how about the sodium sulfate? Well, it's aqueous also, and so we're going to get 2 sodiums, and we're going to get that sulfate polyatomic anion back again. Now, this is the point where you reach it and you begin to look for the spectator ions. Where are those spectator ions? Well, the sodiums are certainly spectator ions. They're present both as products and as reactants. We're not done, though. There is one more ion that occurs in exactly the same fashion on the left and the right-hand side of that arrow. Can you see it? It's the sulfate. Sulfates appear both on the left and the right. There's a single one in both places, and so we have this collection of spectator ions that we can eliminate from the total ionic equation as we create the net ionic equation. What are we going to be left with? Well, there are going to be those 2 hydrogen ions that I started with. The sulfate and the sodiums are gone. The 2 hydroxides, they are not spectator ions, and so we would include those. Then we're going to have to draw an arrow and the 2 water molecules that survive. This is really a beautiful, essential description of the chemistry of an acid-base neutralization reaction. Now, before I gloat over how wonderful this reaction is, let's clean up a few details. You should notice that in all cases I've got a coefficient of 2, and that can be simplified. And so the net ionic equation for this reaction would be H plus OH minus goes to H2O. Since 2 can be divided evenly across the board, we can simplify it and put 1 coefficient in front of each. This net ionic equation, H plus OH minus, producing water, is at the heart of most traditional acid-base neutralization reactions. The other ions, well, they were spectator ions. They had to be there to bring the hydrogen ions in the case of sulfate. They had to be there to bring the hydroxide ions in the case of sodium. But those spectators beyond that point aren't really all that interesting. We eliminate them, and we get to the essence of the acid-base neutralization reaction, which is the combination of the hydrogen ion, the hydroxide ion, and the water that's formed at the end. It's the net ionic equation. Let's finish up this presentation with an example problem. I'll warn you, I'm not going to post the solution to the problem immediately. Rather, I would like you to think about it. The problem involves mixing barium hydroxide, an aqueous solution, with sulfuric acid, another aqueous solution, and I'm asking you what products are formed, and then what are the molecular, the total ionic, and the net ionic reactions. To help you with this, I've posted solubility rules there in the upper right-hand corner that should help you identify the products that are formed. In a later presentation, I'll post the solution as well as the actual experiment as a video file.